know if the microphone is on. Okay, good. All right, so today, last section of Chapter 6, we're working with binomial distributions and geometric distributions. We'll learn about the criteria for doing each of the type of distributions. We have to match certain characteristics. There are other types of distributions out there besides just these two. These are just the two that we focus on in the AP course compared to just normal distributions. There's one out there called a Poisson distribution. There's a multiple kind of a variable distribution as well. So as we look at what a binomial distribution, when the same chance process is repeated several times, we are often interested in whether a particular outcome does not happen on each repetition. In some cases, the particular number of repeated trials is fixed in advance, and we are interested in the number of times a particular event, which is called a success, occurs. If the trial in these cases are independent and each success has an equal chance of occurring, we have what's known as a binomial settings. So here's the definition. We use this acronym BINS as we go through in the proof of a free response question. When we do the do stage of the state plan do conclude. In the plan stage, this is where we would check the conditions. That's where we would check our conditions with the BINS. Do we meet these 4 criteria? A binomial setting arises when we perform several independent trials of the same chance process, record the number of times that a particular outcome occurs. The 4 conditions for a binomial settings are: 1, they have to be binary, meaning the possible outcomes of each trial can be classified as a success or a failure. The I for independent, trials must be independent. That is, knowing the outcome of one trial must not have any effect on the outcome of any other trial. And then the N stands for the total number of trials. N of the chance process must be determined in advance. So before the process even starts, we have to know there's a fixed number of trials. And then S, success, each trial, the probability of P of success must be the same. So it can't change as we do each repetition. It's got to be the same probability every single time. And so sometimes when we look at different situations where with using decks of cards, we pay attention to are the cards being replaced? Because if they are being replaced, then as we do another draw, hey, it's going to stay independent because one drawing of a card doesn't affect another one because I'm putting it back in. That also helps with the probability aspect. When you look at if I keep replacing the card back in that I pull out, then I don't change the denominator at all, and I don't change my probability. Whereas if I pull out a card, put it to the side, then go get another one, now what I'm dividing by the total is different, therefore the same probability percentage is not occurring every time. There are times somebody asked me in another semester, well, shouldn't those go hand in hand, the I and the S? Majority of the time they do. Sometimes when it doesn't, I think we have an example or note, and I'll pay attention, let you know that is sometimes when we switch situations when we're doing like a multiple tier thing. So here's our definition. The count X of successes in a binomial setting is a binomial random variable. The probability distribution of X is a binomial distribution with parameters N and P, where N is the number of trials, P is the probability of success of any one trial, and the possible values of X are whole numbers from 0 to capital N, or whatever our final thing is. So we can see our little binomial distributions like what we did earlier in this chapter, checking the conditions that, hey, each probability's got to be between 0 and 1. We don't have negatives. The sum has to add up to be 1. Again, that's determined a little bit sometimes by how many decimal places you take it out to. But when we go through and on free response, we want to make sure we check the bins to make sure we actually can do what we need to do. So here's an example. For each of the following situations, determine whether the given random variable has a binomial distribution. And then what we use for our justification is we actually use the acronym BINS. So the first one we're looking at for the B, is it binary? So they say shuffle a deck of cards, turn over the top card, let X be the number of aces you observe, put the card back in the deck and shuffle it again. Repeat this process 10 times. So when I look at it, X is the number of aces you observe. So when I look at success, a success would be I see an ace. A failure would be no ace. So that's binary, so we meet the binary clause. Okay, you either saw an ace or you didn't see an ace. Independent, the I. They tell us in here that you put the card back in the deck and shuffle again. So one trial doesn't affect another. So we got independence there. The N, fixed number in advance. They tell us we're doing this 10 times, so N is equal to 10. So yes, that's fixed. And then success, so the S. What is the probability? Well, if how many aces are in the deck? Should be 4 out of 52. So that's 3. 52, which would be 1 out of 13. So, and since I'm putting it back in, then my ace, then it stays the same probability every time that I would see an ace. I got a 1 in 13 chance of seeing an ace every single time I keep doing this process. So that one is a binomial setting, which means as we learn the formula for calculating the binomial distribution or even filling out the table, we could create a table saying we're doing this 10 times. So we would start off the top with saying 0 aces, 1 aces, 2 aces, 3 aces, 4 aces, 5 aces, all the way up to where I happen to see, maybe I got lucky, saw 10 aces. Then we can find the probability that each one of those events could occur. So next example, choose 3 students at random from your class. Let Y be the number of students who are over 6 feet tall. So I'm choosing 3 students at random. So as I look at it, and we're trying to find the probability eventually number of students who are over 6 feet tall. So binary, a success would be 6 feet tall. A failure, not 6 feet tall. The I's, well, here's the thing. I am choosing 3 students at random, and I don't put them back in line. So it's like once I choose the 3. So here, we would actually fail. There's no replacement here. There is no replacement. So we fail independence. So we do not meet the binomial characteristics that we have to go through in order to decide to do this by the binomial calculations, which means we got to figure out some other way. Okay, it just means we just can't use this binomial distribution to calculate it. Next one here says you flip a coin. If it's head, you roll a 6-sided die. If it's tails, you roll 8 8-sided dice. All right, so and we're going to repeat this process 5 times. So we're going to flip a coin. So for binary. All right, so success would be a heads. Failure would be a tails. Now we got a compound probability going here. We got 2 events going on there. And then here's where we kind of have the issue. It's not with the coin aspect. It's actually, well, let's see. For the independence, Does a coin and a die, can they affect each other? No. So a coin toss and die rolled don't affect each other. All right, so number of trials, yes, we said n is equal to 5. Here's where the issue comes into play, is with our success. If I flip a heads, which we know is 1 out of 2, then I have to do a 6-sided die. So that means there's a 1 in 6 chance of me getting whatever number I'm looking for. Okay, what is the chance of flipping a heads and rolling a 5? All right. The problem is, when I look at the tails, yes, it has the same probability for the coin, but then I have to use, if I got tails, I was supposed to use an 8-sided die. Now that's a 1 in 8 chance. And our probability of, like, if we said our event was, rolling a 5, just rolling a 5 is what we were looking for. Well, I got 2 opportunities of rolling a 5. It's either a heads and I roll a 6-sided die, or a tails and I roll a 8-sided die. I can get a 5 on either one, but the problem is the die percentage is not the same on each of those situations. And so that's where we would fail for the success part. For the success clause. Another example would be if we think about a test. If a teacher was given a test that was true and false and multiple choice, typically how many questions are on how many answers are for multiple choice typically? Yeah, with multiple choice you have 4, right? 4 or 5? True and false, we have 2. All right, so when I'm trying to calculate the overall probability of just randomly guessing, well, I can't do it by a binomial setting because the probability changes. We go from 50-50 like a coin to now I got a 1 in 4 chance. And so that's another situation of, whether I guess on this problem, whether it's multiple choice or true false, they're independent of each other, unless you're trying to do a pattern like a Christmas tree or something on a Scantron. But then when you get to the success part, that's where I'm going to fail because I changed the probability for each of the types of questions. So that's another situation where the I and the S, they would be different, and one you'd be okay on the I clause, but not on the S clause. All right. So for any setting in which we are interested in K successes and N trials, remember K is our success. The probability that our event X would equal K means exactly successes. So typically when we see an example coming up here in a little bit, but the purpose of this little part is to talk about is I have options of either X equaling a flat out number. So when we see the equal sign, that means exactly that one event happened. Exactly this one event occurring. The other thing we will see based on if they give us statements with inequalities like more than, less than, at least, at most, we'll see these inequality statements. And this is where we gotta sum up. We gotta sum up a bunch of exact probabilities. And again, we did that in our little tables where they gave us the whole numbers on top and then the percentage of those occurring in the next row. We would say, hey, what's the probability of getting 4 or more? So we just added the probabilities together of each of those, the 4, 5, 6, or whatever it was. So when you see the equal sign, you're going to do exactly that one event. And then when you see the inequalities, you're summing up a bunch of events together. Now, there's a couple different ways we can go about finding our answers to these binomial distributions. They do like on the AP exam, they like having on the multiple choice section, it is more the fundamental format of the formula is how we'll see this kind of thing. They'll give us a situation. We realize that it's a binomial. We look at the answer choices, and we got to figure out which one matches the setup of the formula. On a free response, it's going to be more like later on in the lesson, we can use the calculator format to go ahead and figure out what our answer is. We can do the formula based off of the formula, but it's just typically that's how it's kind of looked at in a way, just looking at examples. You get very few of these that where they just flat out give a decimal answer. It's usually like, hey, can you spot the correct format of the formula to have the setup to do it. So this is what this part is here. A lot of the college textbooks have this little format notation, N over K. Notice there's no fraction there. That stands for a combination. That's the combination formula. We are used to seeing combination from Algebra 2. Oh, shoot. We are used to seeing it as that N, the NK, the N, NCK. That's what we're used to seeing it as. So this is what we see in the calculator. We actually see in the calculator NCR. NCR. And that's how we refer to it. If you press math arrow over to the PRB column, you'll notice I think it's option 2, or is it option 3? One of them permutations, one's combination. I know the first one is RAND, but I think option 2 is the combination. Number 3 is okay. What's number 2? NPR. Okay, so they did permutation before combination. Okay, so that's what we used back when we were doing combinations and permutations back in Algebra 2. So this is the first part of the formula, and we don't use. I mean that's just one part of the formula in the process. And so what we got to figure out is we got to figure out all the different combinations that this could come about doing. Now, I made a little note. You can find it in that one if you forget. Now, once we figure out all the different combinations that could occur, that's almost like the tree diagram. It's almost like creating that tree diagram and all the different branches of these events happening, this one with this one. Then we multiply that by the probability of any one specific arrangement of successes. So down here is the formula, where when I know I meet the binomial probability, I meet the distribution criteria, to find the event, that one event exactly happens, I take the combination of how many different ways it could occur times P to the K, P being the probability of success. So if you want to write that down there, that P is equal to the probability of success. K is whichever event I'm looking for. Hey, the probability of exactly, hey, it happened 3 times or 5 times. So K is actually a physical number between 0 and whatever your last number is. When we do P to the K power, then we multiply it by 1 minus P to the N minus K power. The other way you can use your formula setup is the NCR, or NCK. You can have it set up like that as well. Just changing the format. I know I've seen this first one on different AP practice exams. I've seen that format where we'll see, I'll see a setting, something that looks like this, 5 over 2, and then it'll have, like maybe my probability of success was 20% raised to the 2 power, and then it would be 0.80% or 0.80 raised to the 3 power. And that's how it will look like as a multiple choice answer for doing that one situation. So your bottom number in the first part should match the first exponent, and then the difference between the two numbers should be your last exponent, is what it should be. Okay. So we get to do some problems here. We get to do a couple of practice doing this stuff by hand. Each child of a particular pair of parents has a probability of 25% of having type O blood. Suppose a parent have 5 children. Find the probability that exactly 3 of the children have type O blood. Okay. So let's write down what we know. We know that our desired event is exactly 3. So X is equal to 3. That's our desired event. The probability of having type O blood is 25%. And we know that N is equal to 5. They're having 5 kids. So I'm just grabbing just the numbers from the problem. And then I'm going to go ahead and set up the formula. So the formula again would be N over K. And then it would be times P to the K times 1 minus P quantity to the K. So that would be 5 and then over 3. No line. Don't show it as a fraction. Then times 0.25 to the third power. And then it would be 0.75 raised to the second power. And then that would be my format to calculate my answer. In a moment here, I'm going to go to, and again, if you want to use fractions, they give you fractional situations like the next one. That's fine. We can just leave it as 1/6. Don't turn it into a decimal. I'm going to do a split screen and grab my calculator and put it up there. And we can type that in just the way we see it. Now, the NCR is a little bit different, so I'm going to go into math, over to probability, go down to option 3. I'm going to go smaller there, enter. And then I put 5 and 3 as my 2 numbers, go off to the side. I'm going to do times quantity. Oops, that's not a parenthesis. Quantity, 0.25, close it, raise it to the third power. Get out of the exponent times, parenthesis, 0.75. Raised to the second power. That looks pretty good. And I get that it's approximately 0.0879. Do what?
I was asking, like, why is the other 2?
Why use the other exponent?
No, like, I was just asking where we got 2 from, but I don't know.
Okay, 5 minus 3? Yes. So we have, there is about an 8.79% chance of having 3 kids with type O blood. Exactly 3 kids. Chance of having exactly 3 kids with type O blood. Not a high percentage. I mean, that's, but it's still possible. It's not like microscopic minute. It's still an 8% chance that 3 of the 5 kids would have it. We didn't ask what order. They didn't ask us that kind of stuff. That's a different ballgame. All right. So now, should the parents be surprised if more than 3 of their children have type O blood? So more than 3 would mean I would want X equal to 4 and X is equal to 5 is what that means. So I basically need to say, all right, let's do this with 4 kids. So 5 and then 4, 0.25 to the fourth power, 0.75 to the first power. And then I need to add to that all 5 of them, so 5 over 5. And then it's 0.25 to the fifth, 0.75 to the 0 power. And so I got to add those 2 probabilities together. So I'm going to go back to my split screen. And I'm going to go to my calculator. And again, the challenge part here, it's always the NCR part. That's the combination formula is the harder part to put in there. But I could actually do second enter, back up, and I'm going to start from the far left and say, all right, make that a 4. Change the first exponent to a 4. change the last exponent to a 1, and then I'm going to hit plus. I'm going to do second enter. I didn't like that. Plus, second enter. Nope, it didn't like that. So, oh, it erased it. That's what it did. It changed my stuff. I see what it did. So I can at least put it in there once, change the exponents. But I think, oh, you know what I can do? Always try to find ways to do this. If I go up and grab that and hit enter, then it puts it in there again. I'm so smart. Then go back and change that to a 5. Probably been faster just type it in twice separate. Go into 0. There we go. So now I got them both in there. And I'm going to hit enter. And it says that it is approximately 0.0156. So there is a 1.56% chance more than 3 of the kids are type O. So should they be surprised? I would be. A 1% chance, that's pretty small. So to have 4 or 5 of the kids, all 5 of the kids, to have type O, I mean, that's a slim chance of that happening. So I would be surprised if that was the case, if 4 out of the 5 or 5 out of the 5 had type O blood. All right, next one. When rolling 2 dice, the probability of rolling a doubles is 1/6. Suppose the game player rolls the dice 4 times, hoping to roll doubles. Find the probability that the player gets doubles twice in 4 attempts. All right, so my probability of success is 1/6. And then we know that my x is equal to twice, exactly 2 times. And my n is equal to 4. And again, when I say x, that's also k. K equals 2 if you were looking at the formula. So with that in mind, I need to do 4 over 2. Oops, sorry. That's in the other class. 4, 2 times 1/6 squared times 5/6 squared. Because 4 minus 2 is 2. So 5/6 because, again, 1 minus 1/6 would be 5/6. That's my probability of failure. All right, so we're going to go split screen up here. And again, we can use fractions. If you want to use fractions, you can. You don't want to turn it into a decimal and round because then you're going to be off on your accuracy. So you're safer going through this with the 1/6 and so forth. So I'm going to go math, probability, NCR, and then I'm just going to go 4, 2 times, and then alpha y, alpha y equals, and that's 1/6, and then I'm going to square that, and then I'm going to times alpha y equals 5/6, and square it. All right, that looks pretty darn good. If you want to put the parentheses in there, you can. You don't have to. And that gives me, oh, nice. I love that. Love fractions. 25/216. And we're like, what the heck is that? Math, arrow down to option 2, tells me to put it in a decimal. So that's approximately 0.1157. When we learned how to take a decimal to a fraction, we just said, hey, do math, enter. And that took a decimal to a fraction. So option 2 takes a fraction to a decimal, is what it does. Because we do stuff with decimals. We're not leaving stuff as fractions. All right. So should the player be surprised if he gets doubles more than twice in 4 attempts? So that would be the probability of 3 and 4. All right, so I got to do 4, 3, and then do the same thing like we did up above. And add the probabilities together. 4, 4, 1, 6 to the 4, 5 over 6 to the 0. So I'm going to go back up and grab what I had up here, alter my exponents. So I'm going to do the 3 one first. And plus, go back up, grab that thing again, and then change those to 4 and zeros and stuff. You know, several different ways you can do it. It's just wherever you feel comfortable with. And that would be 0. And then I'm going to hit enter. And I'm going to hit math option 2, enter. And it is 0.0162. So there's a 1.62% chance of rolling more than 3 doubles, more than 2 doubles in the 4 attempts. So I would say yes. It would be. I would be surprised. It's a very low percentage. What happens on traditional Monopoly when you roll 3 doubles in a row?
Jail time.
That's right, you go to jail. If you go by the true Monopoly rules on the box, 3 doubles in a row, you go straight to jail. So, all right. To introduce your class to a binomial distribution, Ms. Desai gives a 10-item multiple choice quiz. The catch is students must simply guess an answer, A through E, for each question. Ms. Desai uses her computer's random number generator to produce the answer key so that each possible answer has an equally chance to be chosen. Patty is one of the students in the class. Let X be the number of Patty's correct guesses. Show that it's a random, that we can do a binomial random variable. So this is where we're doing the bins, is what they're wanting us to do. So for the B, a success, we got the question correct. A failure, it was incorrect. Again, this is what you would do on a free response. But just like that's what you would listen. Just you don't have to be super explaining with sentences. We can just do short stuff here. I'd probably spell out success and stuff is what I would do too. The independent. There was random assignment. Of the answers. And whenever we have random assignment, that allows us to go towards the independence. That assures independence. So random assignment assures independence. How many questions were on the quiz? 10. So fixed number in advance. Success. What's the probability of getting it correct? Just getting a question correct. 1 out of 5. Stays the same each time, right? Sweet. So that's what we needed. Okay. So now they ask us to go through and find and interpret what x equal to 3 is. So we want that they get 3 correct. Okay, so now, can we do it a little bit faster? You okay with trying to learn a faster way? Or do you want to do a long, drawn-out way? Faster? All right, faster. All right, so again, we are doing a binomial. And we have 2 options in our calculator. We have what's known as a PDF and a CDF. When you're doing the exactly, you're doing the PDF. And then again, the C stands for cumulative. So that's when you're adding. So whenever you have any of the inequality statements, so you're doing the greater than or equal to, or the less thans, any of those things, that's when we know we got to do a CDF. When we're seeing the at most and the at least and those kind of things, that means we're doing the binomial CDF. Now we got to be careful, because some cases, as we use those ones, and we'll talk about that as we go. So with that in mind, so for ours here, we're going to do and this is what you would do on a free response binomial CDF. You would actually write down, hey, in your plan stage, using the calculator and the binomial CDF feature, we'll calculate the probability. And then for the do stage, we'd actually write down that format. And then, so I'm going to split screen. To get to it, it is a distribution, so that's in the second VARs category. So second VARs, and it's on the next page. And the PDF is option A, and the CDF is option B. So we're going to use the option A one. And then we would list, okay, trials. We would actually put down trials. We did 10 questions, so N is 10. My probability of success was, you could type in 1/5. Again, it's a terminating decimal, so putting in 0.2 is fine. If we were doing that coin one, where it's 1/6, I would type in 1 divided by 6. Okay, let it calculate all the decimal places out. And then my X value is 3. So I'm going to put 3 as my X value. And hit enter a couple times. And this gives me that it is 0.2013. All right, so now they ask me to interpret it. Let me back that over there, give me more room to write so you can read. There is a 20.13% chance that Patty will get 3 questions correct. Now, here's where it gets a little bit challenging as we're going through this quickly. When we look at these, we know we've been using the normal CDF feature, and we get to adjust the upper and lower bounds for whatever we want to do to find areas to the left, between, or to the right. When we're doing the two things we're learning today, the binomial distribution or the geometric distribution, it only does to the left. Okay, so it's almost like reading the z-score table for the percentages. It's everything to the left of it. So at any time you're doing a situation that requires you to find the probability of something to the right, we got to use the complement rule, is what we got to do, which would mean 1 minus the stuff to the left. So, and this comes into this problem right here. To get a passing score on the quiz, the student must guess correctly at least 6 times. So we're trying to figure out the probability that Patty earns a passing score, which means she's got to get at least 6. So that's greater than or equal to 6 is what my statement is. Now here's where we got to be careful. If we had a nice big table, if we had a big table of values, and we had 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Basically, we would know that, hey, I would add up all the ones from 6 through 10, all those probabilities together. And that's going to be my answer. But we don't have that table. Okay? So now I got to figure out how to get the calculator to do it. It is set up with the binomial CDF feature to only do what's to the left, is what it needs to do. So what I tried to show here by doing the 2 different colors is, notice it's set up to do, if I want to do 6 or more, I need to figure out what 5 and less is and then subtract it from 1. So what I can do for the calculator is I can say, you know what? I'm going to do a 1 minus the probability that x is less than or equal to 5. That's what I'm going to do. Because I want to find my answer, which is 6 and more. Well, I can just use the complement rule and do 1 minus the probability of the 5 and less. So that's what I'm going to use. I'm going to do 1 minus a binomial CDF. My trials, again, is still 10. My probability of success is still 0.2. Now, I want my x value to be 5. I want it to take all the columns 0, 1, 2, 3, 4, 5, add them up, those probabilities, and then subtract that from 1. And then that's what I'm going to type into my calculator. So as I get back to my split screen, I'm going to clear my screen there. I'm going to do 1 minus second vars, option B, which is on the second screen, 10.2, and then 5. Hit enter carefully a couple times, and I get that is 0.0064. So there's a 0.64% chance. Is that a high percentage? Nope. So there is less than a 1% chance that Patty is going to pass by her just randomly picking an answer, and then having the computer randomly generate the answer key and so forth. She's got less than a 1% chance of passing. Questions so far? All right, so when we describe a binomial distribution with center and spread, we describe the probability distribution of a binomial random variable just like any other distribution. We look at shape, center, and spread. Typically, we don't have outliers just because we have a fixed set of stuff. Remember, we got a fixed number of trials, so you're not going to have some random thing out there outside of your biggest number of trials. So that's when we look at the SOX acronym, the outlier is not there because we really don't have one when you think about it. Consider the probability distribution of this one, X being the number of children with type O blood in that family with 5 kids. There are the probabilities that none of them have it. 1, 2, 3, 4, 5. We found some of these by hand is what we ended up finding, those. They asked us to kind of draw in our little picture here, sketch a little histogram, and just describe it, shape, center, and spread. So here we go. So we're just going to quickly get in here and graph it. So there's the first column, something like about that. 39 point, that is somewhere up there. Then 26 right above that line. Then we drop off pretty quickly. And then, so as we look at the shape, what could we probably say about the shape? Yeah, it looks like it's skewed, like skewed right? Skewed right. The center. Where does the mean or median kind of look like? Well, let's see. If the first two categories right here added together, you're looking at about, 63? So somewhere around 1%. So somewhere around one kid. Somewhere around one kid is where we're going to see the center. Approximately one kid. Somewhere around there. Just adding the percent of the data. I was going like since it's skewed, we're supposed to use the median. So that's where I was adding, 23% and 39% technically gives me, 62%. So it's going to be somewhere around that one kiddish mark. And the spread. Well, the spread doesn't really help us because that's just 5. Okay, that's just 5. That really doesn't tell us much. We had 5 kids. That really doesn't help us. If we want to look at the spread of percentages, now we're looking at from 39% down to 0.00098%. But now, what is the mean? Okay. It's not given to us. How can we find the mean based on what we've known so far? When we're given a table, what could we do? How can we find the mean? We learned it last week. That's right, we could. We could go, can we go like L1 and L2? And then do a 1-var stat? All right, so let's do that real fast. So let's get that in there. There, calculate, stat, enter. 0, 1, 2, 3, 4, 5. Get over there. 0.2373. 0.3955, 0.2637, 0.0879, 0.0147, and 0.12389. There we go. And then we go stat, 1-var stat. Frequency list is L2. Hit calculate, and there we go. They tell us that our mean, it looks like 1.2498. So you're looking at about 1.25, something about that. Right around that, approximately 1 kid, I was guessing. Okay. Now, the other way I could do that, can't we take our each individual outcome or each desired event, like 0 kids times the probability below it, multiply those down, and then add up all those answers to find the expected value? All right, so since each child is 0.25, the chance of hearing the program, we'd expect 1/4 of the children to receive that. So again, another way you can get that was like 1/4 times the 5 kids, and that's 1.25. So that's this little part right here. So you can also do 1/4 times the probability, or times the number of kids. We can use this method here, and we're going to talk about that in this next little part here. Instead of having to type this stuff in and do that 1-var stat, because this is a small table. Sometimes we're given like 20 things. So what we can do, and that's what leads us here. If I want to find the mean of a binomial distribution, all I have to do is take my the number of my n value, whatever n is, and multiply it times p. So that would be my probability. So n would be, n is my number of trials times the probability of success. That tells me what my expected value or my mean is. To find the standard deviation, it is the square root of n times p times 1 minus p. And again, these formulas work only for binomial distributions. Other distributions have different formulas you got to use. So they ask us now to kind of practice that skill a couple times. So to introduce her class to binomial distributions, Ms. Desai gives the 10-item multiple choice thing. And they ask us to fit, Patty is one of the students in the class, find and interpret the mean. So again, n is equal to 10. The probability of getting a question correct was 0.2 or 1/5. And so they asked us to figure out, okay, what is the mean of this situation? Mu x would be equal to NP, which is 10 times 0.2, which is 2. So here's the interpretation. After taking the quiz, many times, we would expect her to average to correct questions. Again, we would, if Patty took this quiz multiple times, or any kid, we would expect that their average would be 2 correct. All right, they asked us to find and interpret the standard deviation in context. So again, formula. Standard deviation is equal to square root of NP times 1 minus P. Now, we just found what NP was, the mean. So we got to do the square root of, again, 10 times 0.2 times 0.8. Now, I already have that for us, just to speed things up for us. That ends up being 1.26 approximately. So the interpretation aspect, on average, the number of questions Patty will get correct will vary from the mean. Remember, just like in the earlier stuff, this chapter, go ahead and state what the mean is. The mean of 2 by about 1.26. So the next one, the way they phrase it, is a little bit quirky looking. They ask us, what's the probability that the number of Patty's guesses is not more than 2, more than 2 standard deviations above the mean? And then we got to show our method. Okay, so this would be one of those things on a free response question that they would ask as a little thing. So here I'm going to take a little long way approach. So what's the probability that x is greater than 2 times the standard deviation of x above, meaning plus whatever the mean is? So that's kind of the formula. We got to figure out, well, what number represents 2 times the standard deviation, and then add that value to the mean. And that's what we want to find the probability of, that we're greater than that number. So this becomes the probability that x is greater than 2 times 1.26 plus the mean of 2. That simplifies to x is greater than 4.52. Now, as we write our statement, we can say, since we can't do a partial question, correct. So this is where we can change this to be P of x is greater than or equal to basically 5, or we can say P of x is greater than 4. We can say either one of those kind of statements is how we can convert that to. Either one of those, no matter what, it still leads us to the same process. Since I'm doing greater, I need to start off with a 1 minus on my stuff. So I need to figure out a 1 minus the probability that it is less than or equal to 4. So I wanted to add up the 0, the 1, the 2, the 3, and the 4, and then subtract that from the 1. And that'll be my answer to either one of those statements over here. So 1 minus binomial CDF. Trials was 10.2, and we were putting 4 in there. that works out to be, if you trust me, 0.0328. So there is a 3% chance that the number correct, she guesses, is more than 2 standard deviations above the mean. So there's a 3% chance of that occurring. Now, they didn't ask us to interpret. I didn't write it down. They didn't ask us to interpret it. The binomial distributions are important in statistics. We want to make an inference about proportions P of success in a population. Now, sometimes as we look at what we're doing, sometimes they don't tell us enough information to decide if it's independent or not. And so this is where we have a condition coming up here. So they said, consider suppose 10% of CDs have defective copy protection schemes that can harm computers. A music distributor affects a simple random sample of 10 CDs from a shipment of over 10,000. Let X be the number of defective CDs. What is the probability that X equals 0? Note this is not quite a binomial setting, and the reason why is as we start off and we're trying to figure out like the probability there's no defects, we would start off with 9,000 over 10,000, and then we would multiply it by 8999 over 99, 9,999, and we would keep going down, and we're changing stuff. So what we have here is the binomial distribution gives us a good approximation as long as we don't get a sample of more than 10% of the population. So if we don't know that they're doing replacement, we can use this 10% rule, is what we're going to do. So if they don't specify it, then we take a look at the size of our sample and compare it to the population size. When taking a simple random sample size of size n, little n, from a population of a bigger size, we can use a binomial distribution model to model the count of successes as long as little n is less than or equal to 0.1 times capital N. Or the other way you can think about it is that 10 times little n is less than or equal to capital N. So if they give me my sample size and I say, okay, what's 10 times that number? Is the population bigger than that? An example would be, let's say I want to do a sample of 50 kids here at Beach High School. Well, what's 50 times 10? All right, it's 500, right? All right. Is that less than the population size of Beach High School? Yeah. Okay. So there's 1,400 kids in our school, so we're okay on that part. And here's what they want us to take a look at. As n gets larger, as I go from n is equal to 10, probability stays the same. As n gets larger, what does the histogram basically do? It goes from being skewed to a what? Yeah, we go from being skewed all the way over here to approximately normal. Which means if it's approximately normal, then we can use what feature? We can maybe use a normal CDF in this situation, which helps, okay? But again, when there's not that many in the sample, then, it's going to be slightly skewed one way or the other. I will say this, if the larger the p-value, the probability of success is, it's going to be skewed left. Whereas when your probability of success is small, it's going to be skewed right. If it's 50-50, then, hey, it's going to probably be approximately normal, okay? So that's one thing. If you notice this one compared to the one that we did earlier, one that we did by hand, the probability of success was 20%. It was skewed right. So just to let you know there, higher the probability, low sample size, skewed left. Normal approximation for a binomial distribution. Suppose X has a binomial distribution with n trials and successes, probability of P. When n is large, the distribution X is approximately normal and with mean and standard deviation. So with that in mind, what we can do is to find the mean. We can do NP. And then we would do the square root of NP times 1 minus P for the standard deviation, which means we need to do this. We need to use this in the normal CDF calculator. And again, because they typically don't give us the standard deviation like we did it earlier in the book when we were doing the normal CDF. So hey, we have to calculate what it is. And you can put a square root symbol in that feature of the normal CDF, which may be the most accurate way to do it unless you want to type in about 8 decimals. We can use this approximation as a rule of thumb. We use the approximation when n, our sample size, is so large that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. That's when we can do that. That's when we can use the normal distribution, is if when I go to check if I have my sample size times my probability of success is greater than or equal to 10, and my sample size times the failure percentage is greater than or equal to 10, then I can use the normal approximation model. I can do the normal CDF feature to get my probability. If not, then I can't use it, which means I'm probably using the binomial distribution to figure it out. Okay? Here's an example. We have sample surveys show that fewer people enjoy shopping in the past. A survey asked nationwide random sample 2,500 adults if they agree or disagree with that. I like buying new clothes, but shopping is often frustrating and time-consuming. Suppose that exactly 60% of all adults, U.S. residents, would say I agree. If asked the same question, let X be the number of in a sample who agree. Estimate the probability that 1,520 or more of the sample, and so forth. So let's write down some things. N is equal to 2,500 adults. Our P was 60%. We're trying to figure out the probability that X is greater than or equal to 1,520. That's what we're trying to figure out. So we need to go through and decide, do I meet the criteria for the bins? And if I do, when I go to figure out the calculation part, we can do it's the approximately normal if I meet that 10% condition in the middle. So, or 10 times, NP is greater or equal to 10. So our success is they agree, failure, they don't agree, because the population of U.S. adults is greater than, let's see, they sampled 2,500. 2,500 times 10, 25,000. Is there more than 25,000 U.S. adults? Yes, so we're way below that. So we know we're good, which means we met that 10% condition for independence. So we met the 10% condition for independence. My number of trials was 2,500. The probability of selecting an adult who agrees is 0.6. Check conditions for using normal. So this is an extra thing. We met the bins criteria. We're going to ask, can I do the normal approximation, which makes it a heck of a lot easier in doing our adding up the percentages. So with that in mind, we got to check, is N times P greater than or equal to 10? So is 2,500 times 0.6, which happens to be 1,500, is that greater than or equal to 10? Yes. Then I go over here and say, okay, is N times 1 minus P greater than or equal to 10? So is 2,500 times 0.4, which works out to be 1,000. That's greater than or equal to 10. So since I met both of those, then we may use the normal approximation. I don't have to do a binomial distribution to figure it out. I can use the normal approximation. If I fail one of them, I can't do it. And we're going to find that in it's a lot of different things we're going to encounter from now until the end of the semester. We're going to be using that normal approximation clause there to see if that way we can use a normal CDF. So they asked us to calculate using a normal approximation. So with that in mind, I'm going to do a normal CDF. Lower bound is 1520. Upper bound is something really big. My mean, we said was, we actually find the mean in that first part of the NP. Our mean was 1500. Standard deviation we don't have. I'm going to type in square root of 1500 times 0.4. Now you can put in there 2500 times 0.6 times 0.4. That's fine. But that's what I'm going to type into the calculator. I'm going to do that right here. Looks like we're going to have to split this. I'll extend the homework. We'll have to split this up into 2 days and finish geometric quick tomorrow. It won't take long. And then we get to practice a bunch tomorrow with it. So my lower bound is 1520. Ooh, that's a decimal point. 1520. My upper bound, something really big. And then my mean was 1500. And then I'm going to type in second square root 1500 times 0.4. So again, you can, and I think a lot of times that's the safest way to go, because a lot of times our standard deviation is a decimal, and it's not and we don't want to have it terminating, or we don't have it rounded. We want a big 9-digit decimal so it gets real accurate for us. So I'm going to type that in, hit enter, and enter one more time. And we find out that the probability of that occurring is 0.2071. So there's so we have a 20.71% chance that more than 1,520 U.S. adults will agree. So all we're going to try to do is we're going to try to just finish up this one side right here. And then we can talk about the next part, but we're going to have to do this in 2 parts. So we'll stop after this one, and I'll start a video tomorrow on the geometric. And it won't take us long to get through it. Once we get this one down, geometric is very similar. It's just the different criteria for the conditions. So in a survey of 506 teenagers, age 14 to 18, subjects were asked a variety of questions about personal finance. One question asked the teens if they had a debit card. Suppose that exactly 10% of teens age 14 to 18 have debit cards. Let X be the number, our distribution X represent the number of teens in a random sample of 506 that have a debit card. Show that we meet the approximation of the binomial approximation. All right, so let's go through our bins again. Success. That would be they have a debit card. Failure. No debit card. Independent. Well, they tell us 10% of teens. Well, our sample size was 506. Well, 506 times 10 gives us 50, 60. Are there more than 5,000 teens? All right. There is more than 5,060 teens aged 14 to 18. Okay. We know there's more than that. So then again, that's what I would want. I would want to write that out in the free response part. N is equal to 506. And then probability of success. That's the 10%. Again, we did the 10% for teens because we used it for independence. They didn't say the teens were put back in. We didn't, it was just, we don't know if they're independent of each other, but that's why we did the 10% clause for independence on that one. So now, check condition. We meet the binomial. Now we say, can we meet the approximation? So is NP greater than or equal to 10 and N times 1 minus P greater than or equal to 10. So is 506 times 0.10 greater than or equal to 10. Well, that's 50.6. Yes, that's greater than 10. Then I would go over here and say 506 times 0.9. Is it greater than or equal to 10? That gives me 455.4. Yes. Normal condition met. I have to show both of those on a free response. I can't just say, hey, if the left one, 50, is bigger than 10, the other one, since there's 500, is going to be bigger than 10. I can't do that. I got to show both of those to get credit. So yes and yes, normal condition met. Sweet. Use a normal distribution to estimate the probability that 40 or fewer. So what's the probability that X is less than or equal to 40? So normal CDF. My lower bound would be 0. My upper bound would be 40. My mean is 50.6. Again, when you do the normal condition, the first one you find, the NP greater than 10, that answer to the N times P is your mean. I'd make a little note next to it. Put like mu sub X there. That way when you go to grab your normal CDF, you don't have to recalculate it. You already got it done. Standard deviation now. We're going to do the standard deviation of, again, it's 506 times 0.10 times 0.90. Again, you can do 50.6 in there if you want. And so now I'm going to split screen and grab the calculator. And boom, boom, boom. Second VARS normal CDF. And we're going 0 to 40. And then we had 50.6. And then in my square root, 506 times 0.1 times 0.9. Bah, that looks pretty good. Enter. 0.05812. So there's a 5.81% chance. That fewer than 40 teens aged 14 to 18 have a debit card. And again, we'll do geometric tomorrow. Again, the reason why we try to do the normal approximation clause, if I meet that clause of being approximately normal, I don't have to worry about doing the 1 minus the binomial CDF and adjusting things. I can freely do my upper and lower bounds real easily and stuff. And so that's why we want to check that. If I can meet that condition, that's an easier way to get a more accurate probability answer of the situation.